All right, and so yesterday we had just a brief help session, answer some of the questions that were for the homework that's due tonight by 11:59 p.m. Mountain Time. Were there any other further questions when looking through the homework? I see a no, so everything must be going good there. We're just cruising through this torsional chapter 5 in the textbook. And let's see here. I'm going to go ahead and start sharing my screen. And also, I'm going to go shut the laundry room door. I can hear the dryer running. I'll be right back. And so Monday, we did cover a lot of material in torsion, looking at just the concept of torsional shear stress, the torsion formula, the angle of twist for circular shafts, and both statically determinate and statically indeterminate types of cases. And so all that was updated to D2L, and we'll just kind of continue on. One of the things we'll talk about first is just torsional failure modes. And I have these listed here, A, B, C, and D, but they correspond to the figure in the handout, where A, there's a longitudinal split. You can see it wrapping itself around the length of this shaft. That is something that's common if you're dealing with wood grain structures as well. If you have grains running along the length of the beam or the shaft, developing a longitudinal split. In this case, it was a ductile material that ended up having a torsional split in there. What that's going to do is it's just going to cause even greater angles of twist that develop with that, and greater shear stresses in the process. And so that's A. B is an example of torsional buckling, which is an elastic instability, and it is something that can occur for cylindrical tubes. And so there's a couple things. One, we noticed that the polar moment of inertia, that is really an object's resistance to torsional displacement. So as the J value increases, the torsional shear stress is going to decrease and the angle of twist is going to decrease. And it's kind of interesting. You'll find that the majority of the shear stress is absorbed by the outer portion of the material of the cross section. I think it's something like about 94% of the torque is carried by the outer half of the say a solid rod. And if you were just to remove that inner half, you would decrease the cross-sectional area by 25%, and that would only increase the shear stress by about 6 to 7% on that outer surface if you reduce that. So J really increases as you get the material further away from that center of the cross-section. And so you might think, well, let's just make this a really big diameter shaft with a small wall thickness. This is what can happen then at that point is you end up with elastic instabilities and torsional buckling. So one thing you have to be cautious to realize that there is that potential for elastic instability with cylindrical tubes. On the other hand, engineers make use of this from a drive shaft perspective, where they design this as the weakest link so that the drive shaft fails before any damage occurs to your transmission or any of the other components. It's a lot easier to replace this than the transmission. So that is something that's often engineered into things, finding items that would be better if that failed as opposed to something else, so it's easier to replace. Let's see. The next one, C, is an example of a brittle failure for a torsional loading condition. This is what would be occurring if you took a piece of chalk and twisted it. It would kind of fail in that manner. And with that, the reason for that is brittle materials tend to fail under the maximum normal stress that's being experienced. And those are going to be occurring at 45-degree planes if you're dealing with pure torsion. D is an example of ductile failure for torsion. And that is going to occur perpendicular since that's the direction that the torsion, your maximum shear stress is being experienced is fairly perpendicular to that. And so the interesting thing with that, you probably looked at that in MET 231, 232, or an ME 216, that this is the exact opposite of what you experience for axial loading. And so for axial loading, this would be an example of a ductile failure where they tend not to have these little marks coming out, but they fail at 45-degree angles. They'll usually kind of neck down and then fail at a 45 if it's ductile. And then if it's brittle in axial loading, it'll fail at a 90-degree like this due to the maximum normal stress. And so the type of failure is both dependent upon the material, if it's brittle or ductile, and also the type of loading. So you really kind of need to know both the material type and also the loading when you're doing a failure analysis to determine why a component failed. But again, remember, C is brittle for torsional loading and D is ductile for torsional loading. Next up, we'll go back here. Next, we get into the topic of torsion of non-circular sections. And originally, the shear stress was believed to be proportional to the distance from the central axis. That's what we looked at on Monday, where the shear stress varied from 0 at the center of a circular shaft to a maximum at the outer edge. And we see that that is only true for those circular cross sections. In 1820, it was proved incorrect for rectangular cross sections. That was by a French scientist engineer, Deleuze. And the reason for this is the shear stress is 0 along the corners of the cross section. We have, this is just the cross section, and so think beam going into the page for the length. And so you have 2 free surfaces at the corners. And so with the 2 free surfaces present, that forces the shear stress to be 0 at that point. And so with that, we can define just the parameters for, say, a rectangular beam with a torque T applied to it, a width A height B. And the maximum shear stress is going to occur at the midpoint of the longest side. And the way this is often worked out is that your shear stress at A is your maximum shear stress, and it's equal to the torque that's applied divided by alpha divided by AB squared, where those are just the geometry properties. The twist is usually defined as per unit length, torque divided by beta divided by AB cubed times G. So we kind of see some of the same material properties and things like that showing up in there, but this is just a relationship that's developed from the theory of elasticity, and alpha and beta, the coefficients there, those come from the theory of elasticity as well. And so let's take a look at that. I have a handout from Ugaral. And so we can look at an elliptical section, 2A and 2B. This could collapse down into a circular section if A is equal to B. Equilateral triangle. They give you the same shear stress at A, angle of twist per unit length. And we get to the rectangular section that we've been looking at, where they have our ratio of A to B, 1, 1.5, 2, and then the corresponding beta and alpha values that you can just grab from the lookup table. As this goes to infinity, both beta and alpha go to 1/3. But this provides you then a table that you can use to determine what the shear stress at A is and the angle of twist per unit length, just coming from the theory of elasticity. As you go down further, you get another solid section, a hexagon. And so this table provides you quite a few options there to look at. And then you have some rectangular tubes and elliptical tubes that give you the corresponding shear stress at A, B, angle of twist per unit length. These problems can be solved using the method of shear flow, which is designed for non-circular tubes, and we'll discuss that. But these relationships here can be derived directly from the shear flow method that we'll discuss later. And so this table will most likely only use that for the solid non-circular cross sections when solving problems. There is also a corresponding table in your textbook, and I believe it just has a square cross section, a triangular one, and maybe an elliptical one. There's just 3 of them if I remember right. But they don't have the rectangular cross section, and seeing how beta and alpha vary with that, it's just a straight A over B equal to 1 is all that you have in your Hibbler textbook. So this handout helps out there. And so let's see, alpha, beta obtained from theory of elasticity. You can solve for the shear stress at A, which is your maximum shear stress. You can solve for your theta, your angle of twist per unit length. And then what you're really interested in is what is your actual angle of twist phi that we looked at on Monday. And that just is taking your angle of twist per unit length times the length of the shaft. And so this is really what you're more commonly after is your actual angle of twist in radians. And so just be aware of that table that's there. It gives you the twist per unit length. This theory of elasticity solution is defined as a potential problem, and it has a lot of corresponding implications to other mechanical engineering problems. In the thermal sciences, the heat conduction convection is also a potential problem. torsion of non-circular sections, that's what we're looking at here, and fluid potentials, the velocity streamlines that you look at in fluid mechanics. If you look at the electrical engineering field, they also have their potential problems dealing with magnetism and fields that fall under this category as well. And so there's a cross correlation where there's quite a few of these problems that collapse down into the same fundamental potential problem from that perspective. And so there's that overlap between solid mechanics and fluid mechanics. It's kind of interesting. Your fluid flow can be used to visualize stress patterns. This is solved using Prandtl stress function, just a theory of elasticity method for solving those partial differential equations. But Ludwig Prandtl, he's known as the founder of modern fluid mechanics and developed the fluid boundary layer concept. But he was around in the, that would be the 19th and 20th century, 1875 to 1953. But he started out in the solid mechanics area and expanded that to fluid mechanics. And so this is really helpful in that oftentimes you use more than just circular shafts. You can often use angle iron, square tubing, or square shafts, I-beams, things like that. And so having a methodology to just estimate what the torsional shear stress is beneficial. And so that gives you a table to look up some specific quantities. And now we can get into looking at the torsion of open cross sections. This is defined as a membrane analogy, but can then be used to look at those angle irons, U-channels. A common material that's being used nowadays is the 80-20 shapes, and those are open cross sections, and so it could be used from that perspective as well. But this membrane analogy just carries forward this concept from a rectangular solid section. And so if we start at that point looking at just a rectangular section, we have the torque that's applied about the z-axis as shown here. The axes are set up x down, y to the right, z coming out of the page. That works with your right hand rule, x curling to y, z is coming out of the page. We discussed on the last page that the shear stress goes to 0 at the corners. And so that really requires your shear stress to kind of flow around, skipping the corners. And it's just going to increase in magnitude until it's at the center. It's going to increase in magnitude again when it's at the center of the height or the vertical side. But if we look at that at point A, y is to the right, z is down. You'll looking at that, the arrows are going to the left there, so that would be the bottom side. And with the interesting thing about that is that tau yz max, where you have your maximum shear stress, your tau xz is going to be 0. And same thing when you look at point B on the left-hand side, z would be out to the right, x down. Looking at the way the arrows are going, that would be down due to a positive shear stress acting on that, or positive torque. And then that will give us a tau xz. And so at your location of maximum tau xz, the tau yz term is going to be equal to 0. And so you essentially get to avoid the combined loading concept. the stress at the point of maximum is only the only state of stress present. And so you can look at those two locations separately. The other thing is this is your maximum at A, and so that's the point that you often look at. You're always concerned about what the maximum state of stress is. In terms of a sign on the shear stress, remember technically this would be a negative shear stress because on the positive y plane it's moving in the opposite direction from the positive z-axis, so that would be a negative. Over here on the positive on the positive x plane, the shear arrow was moving in the positive z direction, so this would be a positive shear stress. Again, that's really essential if you're trying to determine where the failure plane is. If you're doing the stress transformations for that to figure out stress on a particular plane. And so the whole membrane analogy revolves around looking at what happens as A becomes much greater than B. And we saw on the handout that as A becomes much greater than B going towards affinity, that beta and alpha is going to go towards 1/3. And so alpha and beta is equal to 1/3. And we can put that back into our expressions for alpha and beta in our tau max formula and see that tau max is going to be 3t over AB squared. And the angle of twist is theta times L, which will give us 3TL over AB cubed G. And so that's true for thin rectangular sections, which is the membrane analogy. And then we can also note, looking at the angle of twist, that we have a TL over G. For circular sections, we had a TL over JG. And what we can see there is that we end up with an equivalent polar moment of inertia, JE, where JE is equal to 1/3 AB cubed. And so we can pose this back to what we knew as the torsion angle of twist for a circular section. We're just finding an equivalent polar moment of inertia for this rectangular cross section. And so we kind of see how things fit there. This concept will be used when we start looking at inconsistent thicknesses along the shape of the cross section. But this membrane analogy can be carried over to torsion of open cross sections then. It doesn't matter that it's not a complete rectangle. When you are dealing with a thin structure, that can wrap around however, and you can still view that as one big rectangle. And so from that definition then for this angle iron, A would be the entire length of the center line, and B would be the thickness. And we're basically just stretching that out to form then a rectangle at that point. But that would be valid for analyzing the torsion of an angle iron. And you can see the same thing for a U channel. A would just be the length of that center line, the dashed line, and B would be the thickness. And so this becomes really helpful in that now you can do just a back of the envelope calculation to figure out what the maximum shear stress is for open cross sections like angle iron, U channels. The 80-20 shapes have the open sections, and you can get a rough estimate of what the maximum shear stress is, what the angle of twist is, or design it so that you can determine what thickness you need, that type of thing. But it's just really an extension of that membrane analogy and the torsion of a solid rectangle, just looking at a really long rectangle at that point. And so that's something you can do with constant thickness, or B is equal to a constant. If you're dealing with a non-constant thickness, an I-beam is also an open section. You process that the same way, but just look at the different thicknesses along the sections. And so I drew an I-beam here. The top and bottom are known as the flanges. The center portion is known as the web. But we have A2, B2 for the length and the thickness of the flanges, and A1 and B1, the length and thickness of the web. And so when you're dealing with non-constant thickness, we can use that equivalent polar moment of inertia concept and then calculate the equivalent polar moment of inertia as a sum of just 1/3 AB cubed, if we go back up there. And so that provides it or presents it in a manner where we can get this down to an equivalent polar moment of inertia. And as a sum for this particular case, it would be 1/3 A1 B1 cubed plus 2/3 A2 B2 cubed, because we have the top and bottom flange. And so they get multiplied, they get added into the sum twice. So you have 2/3 there. From that point, your angle of twist per unit length is your torque over JE times G. Your actual angle of twist is theta times L, so TL over JE times G, just kind of like what we saw previously up at the top here. And so you can calculate your angle of twist with that equivalent polar moment of inertia. For the shear stress, it becomes something where you have to look at your greater thickness is B1 or B2 greater. Because if we look at that 1/3 AB cubed, our shear stress equation had a B squared term in it. And so we're putting J as AB cubed in there, and so we need to multiply by B on the top to get that back down to a B squared. And so your shear stress equation has the BI term in there to compensate for how JE, the equivalent polar moment of inertia, is defined. And so tau max is going to be your torque times BI, whichever is the larger of your thicknesses that you're dealing with, divided by the equivalent polar moment of inertia. And again, this is really just a ballpark estimate of the maximum shear stress based on the theory of elasticity. If you find that you're concerned with the state of stress, your factors of safety are low, it's something you really want to go into computational methods, finite element analysis, to really get a better approximation of what the maximum state of stress is. And with that, it's interesting when you learn finite element analysis, in that these potential problems all correlate with one another. So for fluid flow, heat transfer, the torsion of non-circular shafts, magnetic fields, you can use a fluids solver like Fluent to figure out what the torsional stress fields would be. Likewise, you could use a stress analysis solver to figure out what the fluid flow would be. But in doing so, you really have to have a good understanding of the boundary conditions and how to manipulate the solver to tweak out those solutions. So to avoid that, they've set up the solvers separately. So Fluent works and is applied to fluid type problems. Abacus can do both heat transfer and the stress analysis type problems. And so they have it set up so that the boundary conditions make sense based on the problem that you're solving. But if you're in a pickle and you don't have access to a fluid solver, you could use a stress analysis solver to do that as well. But this membrane analogy only applies when the section is open. We have an example here. Once the section is closed, you have to use a shear flow method. And so I have a picture of a circular shape here with just a slot in it. And so think of this being a shaft running into the page. This is common with the 80-20 where there's slots located in things as well, but you can use the membrane analogy for this scenario. But if it's a full circular tube, you can use shear flow. If it is circular, you can still use the torsion formula. This is an exact formula, the torsion formula, whereas shear flow is going to give you an average value. But I thought I would just kind of show this as an example of when membrane analogy is okay and when you'd have to go to another solution process. Membrane analogy would not apply here at all. And shear flow is intended more for the torsion of non-circular tubes. But we're going to go through an example problem where we just kind of compare and contrast the results of the torsion formula for this shape, the shear flow for this shape, and what happens when you put a slot in, just so that we can see those differences and have some confidence in what the shear flow is providing. So that is the next topic, the torsion of thin-walled tubes, shear flow. It applies to thin-walled tubes with a closed cross-section, meaning that it goes all the way around for a full perimeter. It is intended for non-circular sections, as the torsion formula is exact for circular tubes. The thickness can vary along the length of the beam, or the length of the shaft, or the cross-section. So let's state that again. The thickness is allowed to vary along the cross-section. You can do that, let's see, I think that would be tough to do with the torsion formula. This one here, that would come back further into the integral expression that you would have to use to solve for that. And so if you have varying thickness, I'd probably steer away from the torsion formula and go straight to shear flow. And so this opens up some flexibility with the shear flow method, and then it can handle the varying thickness. One thing it does do is it assumes a constant shear flow Q, which is really just the internal shear divided by the unit length of the cross section. But the one downside is it does assume that there's an average status shear stress through a particular segment. And so instead of realizing the torsion formula, it varies linearly from the inner edge to a maximum at the outer edge. It's just going to see that as a constant average shear stress across the thickness. But that's typically going to be fine when you're dealing with thin-walled tubes. It's not going to develop a great amount of shear stress from the inner wall to the outer wall. And we'll take a look at that in the example problem too. Any questions so far? Let me get this up here and clear all. I guess any questions? All right. Got one no, so we're going along okay. And so first thing we're going to do in looking at the shear flow methodology is refer to a handout 631 and realize that equilibrium has to apply. And we'll go look at that handout really quick, just on the next page here. And so what we have is now the torsion of a thin-walled tube. From the right-hand rule, this is a negative torque that's being applied. But then we look at this differential element that's located in here. This figure always I struggle with in terms of visualizing that properly. V2 is on that free surface on the cross section that you see there. And so if you look, that's kind of that front corner, and then you have B and A. So this is really the free surface. And then as you extend underneath that, you have V1 on the back side, V4, and on the top side, V3. And so it makes it kind of clear when I kind of point out that free surface face where V2 is located on where the torque is acting. The other free surface face is this outer edge. And so that corresponds to this face. And then V4 would be on the back side of that. That's kind of the shape of that. And if we look at that, for example, we have V1 on the top, V3 on the bottom. That shear force on V1 is just going to be the shear stress acting on that surface at A times the thickness of A times that differential length D of X. And so again, the shear stress times the area will give us the V1. And same thing on the top, V3 would be equal to the shear stress on this surface B times TB times dx. And so equilibrium still has to apply. So if we sum forces in the X, we'd have V3 minus V1 is equal to 0, which tells you that V1 is equal to V3. And so this is the best diagram that I've seen that really kind of explains this concept of shear flow and the equilibrium concept of satisfying that based on the varying thicknesses that you might find at B and A. And as we carry that forward then, we have V1 is equal to shear stress at A, TA dx, V3 is equal to shear stress at B, TB dx, and we know that V1 is equal to V3 from equilibrium. When we set these equal to one another, the dx's will cancel out so that we have shear stress at A times the thickness at A is equal to the shear stress at B times the thickness at B. And these terms then, the tau shear stress times the thickness is equal to your shear flow. Q of A is equal to Q of B, where Q is your shear stress times your thickness is your shear flow, and that's going to be units of force per length when you go and do that. Tau is your average shear stress through the thickness, and T is the thickness. The key point to that is that QA is equal to QB, and so Q, our shear flow, those are equal to one another, and so those are a constant. We're assuming that Q is a constant for the cross section, and so that's a key point in terms of being able to solve for the shear flow methodology. I'm going to zoom in a little bit here because I had to kind of crunch things down. If I didn't crunch things down here, I was kind of going to mess up the layout of all my notes that I was kind of rewriting to make them nice. But some of the main things, one, since Q is a constant, tau max is going to occur at the minimum thickness. And so if this is a constant, as the thickness decreases, the shear stress is going to increase. So we're looking at the minimum thickness location for maximum shear stress. Also, your shear stress and your shear flow act tangent to the path. I've kind of shown that here on this figure. I've just drawn a random figure, and then at a given point, your shear stress, tau1 and q1 are going to act tangent to the path. So you know the direction that they're acting under this torque. I did the same for T2, just drawing another location down there. So we know that acts tangent to the path. And what we want to do is then relate this, find the net torque T, and relate this back to the geometry as we did before with our torsion formula. Shear stress was equal to TC over J, C, J both being geometry parameters. So this is defined, our torque is a line integral of our differential force times our radial distance. And if you think about that, that's essentially our force times a distance will give us a torque. So that makes sense from that torque definition sense. And then also our differential force, if we look at that, our QX tangent to the path. And so Q is force per unit length. And so if we multiply by that length ds, we end up with our differential force. So Q times ds will give us our differential force. And we can make that substitution in. dF is equal to Q ds times rho. And that becomes in our line integral Q ds times rho. With that, remember Q is a constant, so we can pull that out of the line integral. And so our torque then is Q times that line integral of rho ds. Realizing that our radius rho to that mean or median line can vary as a function of theta. And so it really depends on how this rho is varying as a function of theta. That's one thing I didn't show in here. We have the whole area within this segment, dA, but this angle here would be d theta from that standpoint. And we'll discuss that on the next page. For this shear flow analysis, it's always based off the center line or the mean line. Your textbook uses that mean line definition. Others call that the median line, the midpoint of that portion of the cross section. But this is just a line integral, and you integrate over the entire boundary. And so I'll kind of talk about what that means here on the next page as well. There is a simplification where it falls out into algebra, but I'll show you what you need to do if you need to integrate as well. And so that may be difficult to integrate based on the cross section that you're dealing with, especially if theta is, or especially if that rho value, the radius value, is changing substantially with respect to theta. But one nice thing is the line integral ds is equal to 2 times the shaded area enclosed by that mean or median line. And so if we go back up, if we look at the entire area encompassed within that mean or median line, that's going to be equal to our line integral. I think I might have, when I transition this, I might have missed a row in that line integral expression. I think we're looking at solving this right there. So I'll double check that with my notes and update that if needed in this handout. But that's equal to 2 times the shaded area enclosed by the mean or median line. And then the corresponding torque then is equal to Q Q times 2 AM. And so that breaks it down into the algebraic expression. It won't take me too long to look back at my notes. Yep, I was right. There's a row that's missing right there. So I'll get that fixed in the notes and updated. And so we have then torque is equal to Q times 2 AM. A of M again is that area enclosed by the mean or median line. And we can then solve for our Q. Our shear flow based on that is just T, our torque over 2 times the mean area. And remember, Q is equal to a constant and is equal to the shear stress times the thickness. And so that is handy in that now we have an expression where we can solve for the shear stress as a function of torque. Torque over 2 AMT gives us our shear stress. And that's going to be a maximum value when T is a minimum value. And so it collapses nicely down into an algebraic form based off of that line integral equaling 2 times the mean area. And if you're dealing with kind of routine cross sections, then it's easier to calculate that mean area. You really don't have to do a line integral at that point. Say if you're dealing with a rectangular tube, I can calculate the area of a rectangle pretty easily. Same thing if you're dealing with a triangular tube. I think those would be far less common, but square tubing is something that is hugely common in just standard applications. And so that gives us now our relationship for shear stress as a function of torque AM and the thickness. The angle of twist, that can be derived from energy methods, where your angle of twist is your torque times the length of the shaft divided by 4 AM squared times G times the line integral of 1 over the thickness as a function of S ds. Again, this is your actual twist since it's a phi value. If TS is a constant, this can pull out from the integral expression, and you just have the integral of ds, which gives the perimeter of that mean or median line. Again, and that's easy to calculate for some cross section as well. And so this one breaks down to an easy expression as well, where if thickness is constant, that can come out, and that line integral is just the perimeter. And so I don't have a variable for the perimeter. When we go through example problems, we'll just write that in as perimeter if we're able to solve in that manner. But what if you do need to integrate either one of those expressions for calculating the torque or the angle of twist? Main thing to remember is that d of s is equal to rho d theta, and that you could look at from this figure as well. ds is the line length, rho is your radius, and d theta would be that small angle for that shaded region. And so this is something you might remember from dynamics, but if you think about that, ds corresponds to, say, the circumference, r the radius, and rho the angle. And so if you think about that for a circular cross section, ds is equal to rho d theta. If you look at the circumference of a circle, rho d theta, it'd be the radius times 2 pi for a full circle. So the circumference is equal to 2 pi r, is essentially what you're getting at there for defining your circumference. But if rho is varying as a function of theta, then you have to do the integration for that. But again, remember ds is equal to rho d theta, and so that line integral of ds is equal to the integral from 2 pi to 0 of rho d theta, then making that substitution in there. And so from the torque standpoint, we have torque is equal to Q times the integral from 0 to 2 pi. We had a rho in that expression for torque, so that gets multiplied by the other rho to leave us with rho squared d theta. And your angle of twist is TL over 4 AM squared G, integral of rho over T d theta around that full 0 to 2 pi all the way around. So your thickness and rho could be a function of theta, and then you would have to integrate through that expression. But I know I'd probably struggle a little bit with the line integral myself without thinking about it. And so I thought it'd be good to relate that back to something that makes sense in terms of what you could integrate if you ever needed to do that. So I think that gives us everything there. I'll just make that update on adding the rho in that expression. Just missed that one. Cleaning up my notes so they're presentable. Now what we're going to do is some example problems. We kind of looked at a few concepts already. We looked at the solid non-circular sections. Those are pretty straightforward, so I don't think we need to do any example problems there. But we then extended that forward to the membrane analogy. We looked at shear flow, and so I thought when I was developing notes many years back, I thought it'd be good to really compare and contrast this with a circular tube, since we can use the torsion formula, we can use shear flow, and we can see what happens when we put a negligible slot in there that is going to cause it to be an open section, and see what impact that has throughout all the analysis methods and what's occurring there. And so this is a compare and contrast looking at all these different analysis methods. But here we're given, we have a 10-inch mean diameter through that center line with a 0.1 inch wall thickness, and it's made of aluminum, where the shear modulus is 4,000 KSI and the maximum shear stress is 24 KSI. What we want to find is the maximum torque that can be applied and the resulting angle of twist if the length of the shaft is 120 inches long. And so we'll tackle this first from our torsion formula, what we learned on Monday. We'll look at shear flow, and then we'll look at the open cross section and see what that means. Another thing you just have to be careful is when you're given these diameters and wall thicknesses, it helps really just to draw a picture to see what's going on, to make sure you calculate your corresponding outer diameter, inner diameter correctly. So our outer diameter is going to be 10 inches, the mean diameter, plus we have a 0.05 on this side and a 0.05 on that side, and so we have to add a full 0.1 inch to find that our outer diameter is 10.1 inch, and the inner diameter is same, 10 minus 0.1 will give us 9.9 inches for the inner diameter. Difference is 0.2, which makes sense. We have a 0.1 wall thickness on each side, and so that is the difference between then the diameters. If you look at the difference between the radius values, that would be your 0.1 inch. Let's see, I'm just going to double check. Does that make sense for everybody? Got the little question, yes, no thing up again. All right, we got some yeses coming up there. And so again, just be careful with that. draw a picture, it's easy to forget the other side when you're dealing with stuff like this. And so torsion formula, tau is equal to TC over J. I've just rearranged this to solve for torque as tau times J over C. And we can plug in our values. Tau max was given as 24 KSI. J is pi times diameter outer to the fourth minus diameter inner to the fourth divided by 32. And then C is the distance from the center to the outer edge, which is half the 10.1, so 5.05 inches, which will give us a torque that can be applied for this of 373.3 kip inch. So that answers the problem from the torsion formula perspective for the first part. For the second part, your angle of twist TL over JG, we can just put our torque in that we just solved. The length of the beam or shaft is 120 inches. We put J in again, pi times diameter outer to the fourth minus diameter inner to the fourth divided by 32 and divided by G, 4,000 KSI. That's going to be equal to 0.1426 radians, which is fairly small. Then we can look at shear flow. Again, this is going to give an average state of stress through the cross section. And so our rho value to the median line or mean line is 5 inches. We're going out to the center. And we can solve this two ways. The first way is with the integration method. I just thought I'd show that. But torque is equal to Q times that integral from 0 to 2 pi of rho squared d theta. And rho is 5 inches, so 5 squared is equal to 25. There's no theta in that expression, so you could technically pull that out of the expression if you wanted to, but if you integrate, you end up with 25 theta, evaluated from 2 pi to 0. And if you plug in those limits of integration, then you have Q times 25 times 2 pi minus 25 times 0. And that term drops out, and we're left with 25 times 2 is 50 times pi times Q. Q again being the shear stress times the thickness. And so our torque then is equal to 50 times pi times the shear stress times the thickness. And we can just plug our values in now and find that our torque is 50 pi times 24 KSI times 0.1 inch being our thickness. And that comes out as 377 kip inch, which is just slightly greater than what we got with the torsion formula. And if you think about that, what's happening is you are calculating an average shear stress for this cross section. And so it's not accounting for the fact that the shear stress is going to be greater as you move out to the outer edge. And so that tells you you can support a slightly greater torque than what you actually can based on the torsion formula. And so this is going to overestimate the torque that can be applied. And so we kind of see how the shear flow formula works, and that it does give a pretty reasonable answer compared to our exact torsion formula. It's only off by about a factor, about 4 kip inch out of 377. So that's roughly about a 1% difference, not a huge difference. And so that's not very alarming. As your thickness increases for your cross section, your difference is going to then increase between your torsion formula and your shear flow method. And so you do have to be cautious about that. Your AM method, where your shear stress is equal to torque over 2 AM times your thickness, can just be rearranged to solve for torque as 2 AM times your shear stress times your thickness. Again, your mean area is just going to be pi times your radius squared, which will be 25 times pi, and it'll collapse out to the same thing, 50 pi times your shear stress times your thickness. And so you see that the algebraic method just gives you the same result as if you were integrating. And so the algebraic one is the path you'd want to typically do if it's a cross section that's easy to calculate that mean area. But that's the same as before, and you get 377 kip inch with the shear flow method. Either way you go there. Note that the shear flow is equal to the shear stress times the thickness. So the shear flow in this case is 2.4 kip inch, or kip per inch. And then your angle of twist, TL times the perimeter divided by 4 AM, which is pi r squared, times G times the thickness. And again, plugging in our values, with shear flow, we found that that was 376 or 377 kip inch times the length, 120 inches times pi times 10. Pi times 10 is the circumference of the mean circle there. So pi times diameter divided by 4 divided by pi times 5 squared, quantity squared. Be careful. Oftentimes students will forget about this squared value here when going through that. So remember, that's AM quantity squared times 4,000 KSI times 0.1 inch will give us 0.144 radians. And so that compares to our torsion formula, which was slightly less than that. And so if we think about that, we estimated a higher torque that's being applied, and so that resulted in a higher angle of twist being estimated out using the shear flow method. Let's see, I think we have 3 more pages to go through. Would you want to, let's see, let me go back here. Would you want to break now, or do you want to just keep going through the last 3 pages? Do you want to break? I got a no, got bunches of no's. Everybody wants to power through it, so we'll go ahead and power through it. And so the next thing is going back to the membrane analogy. What if a slot is added? We can see how detrimental that is to the torsion carrying capacity and the resulting angle of twist. With this, we can say that the slot is of negligible width, which means the length of the mean line, that circumference, is approximately equal to the perimeter. And so we can make that approximation in the analysis there. With that being the case, A is the distance around the length of the median line, so we can say that's the circumference, pi times diameter, which would be 31.4 inches, and B is equal to our thickness is equal to 0.1 inch, if we relate that back to the membrane analogy. If we look at that ratio of A over B, we get 314, which is well above 10, so we're well into the membrane analogy area. And your shear stress at A then is equal to 3T over AB squared. And we can rearrange that to solve for the torque. Shear stress at A times AB squared over 3. Plugging in our values, 24 KSI, 31.4 inches for A, and 0.1 inches for B. That quantity squared divided by 3 will give us the torque that can be applied to this circular tube with a negligible slot as 2.51 kip inch. And at that point, the shear stress would reach 24 KSI. And that's in comparison to the 373.3 kip inch that could be supported by a fully closed circular tube. And so we kind of see that there's a hugely dramatic impact of just adding a slot along the length of the shaft. We see the same thing with the angle of twist, 3TL over AB cubed G. We plug in our values and run that through, and we find that the angle of twist is 7.2 radians, which is about 2 pi. If we were to apply the 2.51 kip inch and twisted that 120 inch segment, it's about 1 full rotation that would occur on the opposite end under that torque, compared to something that's about 0.14 radians if it was fully enclosed. And so we can look at those ratios, the torque closed versus the torque open, 373.3 divided by 2.51, it's 148.7 times greater the amount of torque that can be applied to the closed cross section. And closed versus open, it's just a fraction, about 0.02 of the angle of twist that you would expect. If we were to do the inverse of that, that's 50.5. And so the twist for the open section is about 50.5 times greater, even though the torque open is, for the open section, is 148.7 times less. So we get this really huge angle of twist out with a much smaller torque that's applied to it. And so that's something that you should be aware of, especially with the 80-20 structures that are commonly being used. If you have those subjected to torsion at all, you really need to evaluate what is that angle of twist going to be. It could be substantial. If you're just using those for axial type loading conditions, there's not going to be that detrimental aspect to that. Here's another example of how shear flow was intended for non-circular cross sections. And so that previous example is really just to compare and contrast the torsion formula, shear flow, and what happens when you put a slot in, looking at the membrane analogy. But for a circular tube, you're generally going to use your torsion formula to solve for that. In cases like this, where we have a triangular tube with the following mean dimensions, we have to use shear flow because the torsion formula would not apply here. But that last example then gave us confidence that our shear flow methodology gives us a nice approximate solution to the state of stress. And so for this particular problem, we have a triangular segment, a torque that's applied. We have 200 millimeter sides, so equilateral triangle. The length is 3 millimeters. I did some conversions already. That's 3,000 millimeters. The torque is 500 Newton meters, which is 500,000 Newton millimeters. And our shear modulus is 75 gigapascals, which is 75,000 megapascals. And so I'm using Newton millimeters and megapascals for the units. For this case, we're given two constraints. We're given the constraint that the allowable shear stress is 90 megapascals and that the maximum angle of twist desired is 0.002 radians. And what we're asked to find then is the minimum thickness. And so there's a strength issue, and then there's a stiffness, torsional stiffness issue. And so we really need to figure out what is the thickness required for either one of these scenarios, and go with the greater of the two thicknesses that come out of that analysis. And so this triangle represents the mean line, the actual triangle material, the thickness would be equally split across that shape. And so analysis using the shear flow method, again, this is the process that you would go through. We can calculate the mean area pretty easily. That's 1/2 the base times the height for the triangle. So the height is 200 times the sine of 60, with that being an equilateral triangle. Will give us a mean area of 17,320.5 millimeters squared. I rearranged the shear flow formula to solve for thickness instead of shear stress, just alternated those around. And so our thickness is equal to the torque over 2 times the shear stress. And we end up with 500,000 Newton millimeters for our torque to our mean area that we just calculated, and our allowable shear stress, 90 megapascals. Will give us a thickness of 0.16 millimeters. This one I did draw or write out the original equation for our angle of twist, TL times the perimeter over 4 squared GT, since T is a constant that we're looking for. And we're just rearranging for solving for thickness, TL times the perimeter over 4 squared G times phi. Plugging in our values again, torque 500,000 Newton millimeters, length 3,000 millimeters. Perimeter is just the sum of the three sides, 200 millimeters each. So 600 millimeters for the perimeter. A of M we calculated, don't forget to square that term. 75,000 megapascals for the shear modulus, and 0.002 radians for our maximum angle of twist allowed. And what we find is that thickness has to be equal to 5 millimeters. And so with that, the thickness to satisfy stress only needed to be 0.16 millimeters. For the angle of twist constraint, it needed to be 5 millimeters. So we have to go with the greater of those two estimates and go with the 5 millimeters. And so the constraint on stiffness limited the design to make that a bigger cross-section and a heavier cross-section. The resulting shear stress is going to then be far less than the 90 megapascals that is allowed. And so that's kind of the process for using shear flow just for normal non-circular shapes, and using the mean area method. And then the last page on that, we'll look at that logistical issue for open sections again. If we put a slot of negligible width in there, what if we have that and we have to do the membrane analogy to figure out what the minimum thickness is? And so the problem remains the same. We've just added a slot there. Analysis, shear stress at A is equal to 3T over AB squared. And so we can plug our values in, just solve for B, 5.27 millimeters. And then angle of twist, 3TL over AB cubed G. Plug in our values again, solve for B, comes out as 36.8 millimeters. And so we see our stiffness again is the constraint that is determining the design. And so we see that instead of 5 millimeters, it needs to be a little over 7 times thicker when we add that slot in there. And if we look at the corresponding ratio of A over B, that's 16.3, which is just slightly greater than 10. And so the membrane analogy is still good, but it's getting close to that limit where it's becoming a really thick cross-section to be able to use that. But with that, you really kind of see the really increased design requirements if you have an opening, a slot running along the length of your cross section. It's not really able to support torque as as easily. You're going to have to increase the thickness by a factor of 7 in order to do so. But that really kind of finishes out our chapter on torque. We kind of made it through that material pretty quick. But I think it kind of helps being able to see that across 2 lectures, you're able to see how those things relate to one another without having that span multiple lectures through the regular semester. But let's see. Is everybody good with understanding the torque concepts with torsion formula, non-circular sections, shear flow, and the membrane analogy? All right, we got some yeses there. I'm still going to show you a trick. At this point, it's fairly clear on the different scenarios, but it is really helpful to kind of summarize this in a table so that in the future, when you're kind of looking at different torsional problems, it's kind of a little bit easier to realize which method you have to use. Because if it's been a while, sometimes it can be difficult again to remember which method you use for which case. And so I always advise students to get a table together. Pretty sure I do that without notes on the board to show students. And so I think I'll have to get that into a note page to share with you as we're getting through this process. But with that, the homework 1 is due tonight at 11:59 p.m. Mountain Time. That's over the first content we looked at last week. I just posted the homework for this torsion material that'll be due on Monday next week. I figure that gives some time to start looking at those, asking questions on Friday. You could still have some time to answer questions or ask questions on Monday next week before that's due at 11:59 p.m. And that'll get us squared away so that we're ready for exam 1, which should cover both of these 2 homework sets. But same thing as homework 1. There are a lot of problems. Normally these would be spread out between 2 different homework sets, but since summer is about half as long, they get kind of combined together into one big homework set to get through the same amount of material. And so with the homework that's assigned for Monday, don't wait till Sunday to start doing those, because it's going to take, I would say, in that range of 5 to 6 hours would be my guess, to get that homework completed, would be my thought. Maybe even more than that. I guess if we're looking at 2 to 3 hours per lecture period outside of class, you're kind of looking at around anywhere from, I'd say, 6 to 12 hours for getting these homeworks done. Let's see. That would help me know. For this last homework problem that you were doing, was that taking more around the 6 hours? I don't see any yeses or nos there. Was it taking a little bit longer, around 10 hours? We got some yeses around that. So yeah, I'm kind of guessing you're looking at that range of 10 to 12 hours for getting through those homeworks. And what I'll do is you're uploading those to D2L, and I'll look at those and provide a grade for that. And then I'll also upload the solution from the textbook for those problems. In some instances, I might add in some other work that I've done just to show the solution there if I don't feel the solution manual is adequate. But for the homework that's due next Monday, let's really get that in on time. That way I can post the solution next Tuesday, and you have a chance to look at that prior to class on Wednesday in case you have any questions that you want answered while you're getting started on exam one there. But that'll help kind of resolve any lingering questions as you're working on exam one there. Are there any final questions at all? Okay, we'll call that good then. I'll stop sharing my screen here, and we'll get this posted to D2L. I'll make that one update that I mentioned for our notes. I missed the row value there, and then we'll see you on Friday. We'll probably just touch up a little bit on torsion, looking at that nice table that I recommend, and then we'll continue on looking at beam bending as our next topic. But we'll call that good